looking at the Coconino Plateau hydrogeology. So now let's look at some of the research that's currently going on in regards to springs and seeps. And I'm going to start with a look at springs classification. So a spring is a spring, right? Well, in the sense that they're all locations where groundwater is being intercepted at the Earth's surface, then yes, they are. But we can subdivide that greatly using a number of different variables. Now, Springer and Stevens have identified 12 different types of springs that can be identified throughout the entire world. 10 of these can be identified within Grand Canyon. And on top of that, each one of these spring types supports a number of different microhabitats that I won't really get into tonight, there's not enough time, but just to let you know so you have an idea of how complex these sites can actually be. Now I'd like to quickly go through the types that we can find in Grand Canyon. I'm going to show you a general schematic of the spring type and then a couple photos from the field. Now in these future slides, the schematics, the A is referring to the aquifer system that's supplying the water to the spring. The I represents an impermeable layer through which groundwater cannot travel. The S represents the spring itself. And then if there's ever any arrows or something, they represent faulting in the rocks. So the first type is a Rio spring, probably the most commonly found spring in Grand Canyon, which just emerge into one or more stream channels, such as the one here at Spring Creek and then also down at Hermit Creek. The next type, which is also fairly common in Grand Canyon, is the Hanging Garden, which is also thought of as kind of the quintessential desert southwest spring type, where flow emerges, usually horizontally, along a geologic contact, along a cliff wall of an unconfined aquifer. And before I get too far along, when I refer to an unconfined versus a confined aquifer system in these later slides, what I mean is whether that system is either bounded on one side by one of these impermeable layers or on both sides. For example, in this schematic, this spring is being supplied by this aquifer system that's bounded below by this impermeable layer, but is open to the ground surface on top. Had this spring been supplied by this sandstone unit here, sandwiched between these two impermeable layers, then that would have been a confined aquifer system. Cave springs emerge in a cave environment with very large conduits. Now these have the ability to transport large amounts of water very rapidly, so you often have a really large annual variability in discharge at these kinds of sites. The examples from Grand Canyon include Angel Spring, which is the source of Bright Angel Creek, and Abyss Spring, which is located up in the Shinneman drainage. Gushette springs are formed from discrete flows that gush from a wall, and we can have a large range of sizes of these types of springs. From this little guy located in Shinneman Creek, a little bit larger, the source of Monument Creek on the south rim. Okay, so even bigger at Basin's Paradise to the absolutely huge at Thunder River. Helichrine springs emerge from a low gradient wetlands. They're often have indistinct or multiple sources and seep from shallow aquifer systems. This is Neil Spring up on the north rim, forms a very nice marshy wetland and supports a nice willow stand. Hill slope springs emerge from aquifers on a hill slope, creative name, and often also have indistinct or multiple sources. This is Fawn Spring. Linda Crean springs emerge from a confined or an unconfined aquifer in a pool or a series of pools. And fountain springs, which are artesian springs with pressurized carbon dioxide that are being expelled from a confined aquifer system. This one is cutely named Vulcan's Bidet and located along the Colorado River a few miles downstream from Lava Falls Rapid. Hydrocrene springs are buried springs where the flow doesn't actually ever reach the Earth's surface, typically due to a very low discharge and either a high evaporation or transpiration rate. As we can see in this little schematic, it's this grove of trees that's transpiring this water before it actually has a chance to be exposed to the Earth's surface. Now the example in the canyon is located at mile 70 along the Colorado River. And rather than a grove of trees, this one is covered in sawgrass and rattlesnakes. The mound-formed spring emerges from a mineralized mound, typically travertine, and is frequently associated with magmatic or fault systems. This is Pumpkin Springs that some of you may recognize if you've ever been down to Colorado on a river trip. Definitely has magmatic signatures. It bubbles with a number of very distinct gases that have mantle signatures, and the water contains a high level of arsenic, and it's actually the highest temperature spring in Grand Canyon. I measured it at almost 90 degrees Fahrenheit this past February. And so those are the 10 that are found in Grand Canyon. The only 2 that have been described that don't occur there are the geyser, which have explosive flows of hot water from confined aquifer systems, your typical Yellowstone scenario. There just really isn't a large geothermal presence anywhere near the water table to have these occur in Grand Canyon. And then finally, exposure springs, where you have caves or sinkholes where an unconfined aquifer is exposed near the Earth's surface. Once again, don't have those in Grand Canyon just due to the depth of the water table in most places. It just doesn't have a good environment for those. But it's still pretty amazing that Grand Canyon can hold 10 of the 12 that can be described in the entire world. Now, moving on to more of a data collection mode, I'm going to talk some about the use of gauges and spring monitoring visits to collect hydrologic data and to add to our understanding of springs and seep systems. So I'm going to start talking about continuous recording gauges. Now, this is really the only way for us to gain enough data from a really remote site to make any sort of confident inferences or statistically significant analyses on water data. So Grand Canyon operates 3 gauges along the South Rim which monitor spring flow over time at Hermit Creek, Cottonwood Creek, and at Indian Gardens. These locations were installed by the USGS in the mid to early 1990s and are still operating today, albeit in a slightly modified form. Since then, new sites have been added at Roaring Springs on the North Rim in 2008, and at Shinnemoo Creek last year in support of the Humpback Chub Translocation Project. There's more coming. I plan to install at Topek's Creek, Kanab Creek, and perhaps some other locations in the next year and coming years. In addition to gauge sites that are continually monitoring spring discharge, there are precipitation gauges looking at the spatial distribution of precipitation rates and intensities, air and water temperature loggers, and water chemistry loggers. The site at Shinnemoo Creek not only is looking at spring flow over time, but it is also measuring water temperature, air temperature, electrical conductivity, dissolved oxygen content, and other things. So, as great as these gauge sites actually are, they're no Ronco rotisserie oven, where you can just set it and forget it. They require a lot of work both in the field and once you're back in the office again. Now, some of these difficulties include the remote locations in which they're installed and the extreme climates to which they are exposed to, including anywhere from below freezing to triple-digit temperatures with electronics stuck in hot metal boxes. The limited amount of visits that can be made to these remote spots also pose problems in the building of a rating curve for these locations, as well as memory problems with limited amounts of memory at these sites and the volatility of the memory of these older systems, where you'd lose all of the data that was collected if the power to that system was lost. Other difficulties include channel changes, both ones that occur slowly and over time, as well as the ones like you saw on this previous slide, where you have them occur at instantaneous events such as flash floods. The sensors themselves tend to drift over time, and that needs to be taken account of. And then finally, there's just a massive amount of data that these things generate. We're talking about tens of thousands of lines of data that need to be collected, corrected, and then interpreted and made some sense out of. Now here's a typical gauge setup, such as the one that the USGS installed at those 3 locations on the South Rim. This is at Indian Gardens. The pump house spring is up here a little ways, flowing downwards into this control pool that was built up with a staff plate right here, so we can make a manual measurement of the height of the water within that pool. And this stilling well contains a little float and counterweight system that moves up and down with the level of the water in that pool and sends a signal off to this box, which contains a number of fancy electronic things, including data loggers and control modules